All right, let's dive into something that you probably think you know like the back of your hand, Newton's laws of motion. I mean, we all learn them in school, right? But what if I told you that our everyday intuition, our gut feeling for how the world works, gets these fundamental laws, well, completely wrong? We're going to see if we can rewire our brains just a little bit to start thinking like a physicist.
So let's start with a classic. Picture this, a hockey puck sliding across a sheet of ice that is so perfectly smooth there's zero friction, none at all. After someone gives it a push, what keeps it going? Is there some kind of lingering forward force? Is it the momentum of the push? Whatever your gut is telling you right now, just hold on to that thought. Because the answer to this one question, well, it's the key to everything we're about to talk about.
You know, if you stumbled on that last question, you are in very good company. Our brains are wired for the world we actually live in. A world that's just full of friction and air resistance and gravity. Think about it. To move a heavy box across your living room floor, you have to keep pushing it. So our brain creates a simple little rule. To keep something moving, you gotta apply a constant force. But in the pure, clean world of physics, that simple rule is the source of so many misconceptions.
In fact, it's so common that researcher Derek Muller actually identified the biggest hurdles people face. And here are the top 5. Today, we're going to zero in on a few of the heaviest hitters. This idea that motion needs a constant force, the huge confusion between velocity and acceleration, and another common myth about what it really takes to make something speed up.
So let's start with that first one, the most powerful misconception of them all, the one that our friction-filled world teaches us every single day. This is the big one. It just feels right, doesn't it? I mean, to keep your car at a steady 60 miles per hour on the highway, your engine has to constantly work, applying a force. But what you're feeling there, what your engine is actually doing, is fighting against friction from the road and air resistance pushing back. In a perfect frictionless universe, this statement is totally false.
And here's why. Newton's first law, also known as the law of inertia. Now listen closely to what it says. An object in motion stays in motion with a constant velocity unless an outside force messes with it. It does not say that motion needs a constant push. So let's go back to our hockey puck. What keeps it moving? The answer is nothing. Absolutely nothing. Just its own inertia.
And that leads us to this really crucial concept called dynamic equilibrium. It's when all the forces acting on an object completely cancel each other out. The push equals the friction, the lift equals gravity. You get the idea. The net force becomes zero. And when that net force, the sum of everything, is zero, an object that's already moving will just keep on moving, exactly as it was. That's the key. A zero net force means zero change in its motion. Check out this football kick. It's a perfect example. The second that ball leaves the kicker's foot, what force is pushing it forward through the air? The answer, again, is none. If we ignore air resistance for a second, its forward motion is just pure inertia. Sure, gravity is pulling it down, changing its vertical motion, but its horizontal speed stays the same because there are no horizontal forces acting on it anymore.
Okay, so we've tackled the idea that you need a force to keep something moving. Now let's clear up another major mix-up, the difference between going fast and getting faster.
We tend to use the words velocity and acceleration like they're the same thing, but in physics, they're worlds apart. Velocity is just your speed in a particular direction. Our hockey puck, cruising along at a constant speed, has velocity, but it has zero acceleration. Acceleration is any change in that velocity, so speeding up, slowing down, or even just turning a corner. And here's a fun little brain twister for you. When you toss a ball straight up in the air, right at the very peak of its flight, its velocity is zero for just a split second. But is it accelerating? Oh, you bet it is. Gravity is still pulling it down, which means it's accelerating downwards even when it's not moving at all. Wild, right? And that brings us to the main event, Newton's second law. This is probably the most famous equation in all of physics. It is the master key. This little formula is the mathematical bridge that connects force, an object's mass, and the acceleration it feels. It tells us exactly how motion changes.
Now, you might sometimes see this fancier, more formal version of the law. Don't let it scare you. All it's really saying is that a net force causes a change in something called momentum, which is just a fancy term for an object's mass times its velocity. For most of the things we deal with every day, where the mass stays the same, this just simplifies right back down to the classic F equals ma.
So let's break this down. That little Greek letter sigma, that C in front of the F, it is so important. It means the sum of. So we're not just talking about a single push or pull, we're talking about the net force, the grand total after all the forces have been added up. Then we've got m for mass. And remember, this is not weight. It's a measure of inertia, that same resistance to change we saw with the hockey puck. And finally, a for acceleration, the change in velocity that you get from that net force. And knowing that brings us to another one of those intuitive myths. It kind of feels like to keep something accelerating, to keep it speeding up at a steady rate, you'd have to push it harder and harder and harder. But let's look back at that formula we just met. F equals ma. The relationship is as clear as day. If the mass, m, is constant and you want a constant acceleration, a, you must apply you guessed it, constant net force, F. Pushing with a bigger and bigger force would give you a bigger and bigger acceleration. To get a nice, steady, unchanging acceleration, you need a nice, steady, unchanging net force. It's really that simple.
So we have these incredible laws, but how do we actually apply them to real-world problems? How on earth do you keep track of all the different pushes and pulls happening at once? Well, physicists have a simple but incredibly powerful tool to help us see all these unseen forces.
The answer is something that is absolutely essential for any physicist or engineer: the free body diagram. It sounds complicated, but it's just a simple, standardized sketch that lets us visualize all the external forces acting on one single object. It's how we turn a messy, real-world situation into a clean, solvable F equals ma problem. And to do it right, there are rules. Rule 1. Every force starts from a central dot that represents our object. Rule 2. Forces are always straight arrows, no curves. Rule 3. You have to label every single force, no exceptions. Rule 4. The length of your arrow actually matters. It represents how big the force is. And Rule 5, and this is the one everybody messes up at first, you only draw forces. Never, ever, ever draw velocity or acceleration on your free body diagram. Those things are the result of the forces, they are not forces themselves.
Okay, let's look at a textbook case. A block just sitting on a ramp. This diagram shows every force perfectly. First, you've got the force of gravity, Fg, pulling straight down toward the center of the Earth. Next, the ramp itself is pushing back. We call that the normal force, Fn, and it's always perpendicular to the surface. And finally, what's keeping it from sliding? That's static friction, Fs, pointing up the ramp, opposing the slide. See how every arrow is labeled, straight, and starts from the center? That's a textbook diagram.
And to really get good at this, it helps to know all the common traps. Don't just label gravity as g. Remember, g is the acceleration due to gravity. It's not a force. And don't forget to include all the forces, even the ones that cancel each other out, like gravity and the normal force on a book just sitting on a table. And a pro tip, if you need to break a force into its components to do the math, do that on a separate sketch, not your main diagram. Keep it clean.
So, we've busted the myths, we've learned the tool of the trade. What does this all add up to? Well, it's really about a fundamental shift in how you see the entire world.
If you take only one single thing away from all of this, please let it be this: that intuition our brain is built on is just wrong. Objects don't need a cause to keep moving. They need a cause, a net force, to stop moving or to change their motion in any way at all. And that, right there, is the single biggest mental leap you have to make to understand mechanics.
And once you make that leap, it leads you to the physicist's mindset. When you see something move, you stop asking what's pushing it. Instead, you start asking what are all the forces acting on it? And then, do they all add up to zero? Or is there a net force causing it to accelerate? That's the process. That's how you use Newton's laws.
So let's end on this thought. Right now, wherever you are, you're not accelerating. But you can feel the force of gravity pulling you down. So, what's stopping you from falling through your chair, through the floor, all the way to the center of the Earth? What unseen force is pushing back up with the exact same strength? Thinking about that, well, that's your first step to really seeing the world like a physicist. Thanks for tuning in.